I will try to present, let me say, just to give an idea of the project, because we have only 8 minutes. And of course, me and the consortium, we are available to provide more details in other calls, in other days. No problem for this. Okay. Just a little bit the outline. So I will give project motivation, very short, the main concepts of the project. I will talk about the use cases. We have 3 use cases in this project. The first results of the project is finishing in end of November of this year. So now we are in the last mile, let me say, in order to converge to the final results and the demonstrators. And then I will conclude. Very sorry. Okay. Very short. The project is on circular economy. So circular economy is moving away from the traditional take, make, use, and waste model, in which we have a linear process. We take resources from the ground, we make a product, we use the product, and then we waste the product. So we can recycle the product after the use, we can return the product and again to make another product, or we can reuse the product, we can repair, and so on. So you see that a product, let me show with the laser pointer, okay, is not having a linear flow, but it's a non-linear flow, because after the waste can come back, after the use can return to make. So we have what we call a circular economy, that is a non-linear value chain. In this circular economy, the project exploits some novel hardware technology that allows you to this non-linearity, allows you to recycle, for instance, the plastic, allows you to reuse a certain product. Of course, we need also this novel hardware technology in order to move from linear to non-linear. The main features of these non-linear circular economies are that we must be efficient in the use of resources. We are increasing the life of the product, so the longevity of products. So we have products that live longer and longer. We are closing a loop, because you see that we have circles, and every time you have a circle and you want to evaluate the performance, you have a lot of correlation in the variable you want to estimate. And then you have a stochasticity here. So these are the main features of this circular economy. And so we are studying in the project the short loop from consumption again to production, the medium loop of the products, and the long loop. And just I will be short here. So first of all, when you have a product that comes back to production, many times you don't have the composition of materials and components. So this is a kind of a first stochastic source in the system that we have to manage. A second source is the time when the product is used in the consumption fine by the user, or the product can be a car, can be a bicycle, can be anything, okay, a notebook. Then the consumption phase is stochastic, because it depends on how much can be used the product. And so the concept is that if we get information along the consumption phase, so along life cycle of the product, then the prediction of, we call the return time, when the product comes back, for instance, to the production, this return time is a random variable, is a stochastic. But if you get information along the consumption phase, then the variability of this return time will decrease, and we can make a better prediction. Also, stochastic is the quality level of the product, because when it comes back, the state can be, it's not known, and also the cost to refurbish or to recycle. Here, in this context, digital twin is seen as a business accelerator. Here you see some references for the circular economies, but we know that digital twin is not a simple technology, so we need high skills a high implementation cost and high maintenance cost for managing the digital twin over circular economy. And so here is the project mainly. We are building a digital twin for supporting the companies to make green decisions when a non-linearity can happen. So when I started the short loop or the medium loop and the long loop. So the digital twin is representing this phenomenon, and it is supporting in what we call the green gateways with the prediction, evaluations, and what-if analysis. This is the platform that we are building. I will fly on this. And let's talk about the use cases. First use case is about plastic recycling, PET. So after the consumption, plastic comes here and then it can come back virgin. So you can have infinite loops with this new technology with the patent of this company. And in AUTOTWIN, we are building a digital twin of the plant of the recycle. Sterilization process in the hospital, they said the tools used in surgery can be repaired, okay, or can be refurbished or can be recycled. And we are studying the repair. Let's say it is a repair is a kind of sterilization. It's a shop floor, like in manufacturing. And so we are using the digital twin to efficiently use the resources here. The third is related to batteries in electric vehicles, and we are building a digital twin of the battery to support for maintenance. Here are the three pillars of AUTOTWIN. So from data, we build the models of the digital twins that will be used. And then using these models, we make decisions. So the goal of AUTOTWIN is to move from data to models mainly, and from model to green. And particularly the models that we build, here you see a PetriNet of a system, are built directly from data. So the main claim of AUTOTWIN is that we are able to generate from data automatically the models of a discrete event simulation that is the technology used in our digital twin. And then we come back. Here, I show to you our main concept. The physical system is operating here. You see, this is a chemical plant. The data are collected by sensors, you see here. And then we have a data schema of the data. So this is a kind of ontology or explaining the data. And then the data are manipulated, aggregated for mining, let's say. And then from this data, we have what we call a knowledge graph, a system knowledge graph in which each node is a data and each arc is a relationship. And then from the knowledge graph, we are able to discover a graph model like this. This is a graph model of the system. And then from the graph model, we converted the graph model into a software, a simulation model in a software environment. Okay, and this simulation model for us is the digital twin that has been built automatically from data. So you see from plant to the data, and then we discover the graph, and then from the graph we have the software. This is from model creation to validation. Of course, so we have the validation, we have the calibration of the model, and all this stuff that is almost automatically, not everything automatically, because you see we are using a domain knowledge here. Just to show to you the models from the knowledge graph, you see I can have a graph model of the system. I can build a PetriNet of the same system. These two models are equivalent. This is a kind of example of a pizza production line. From the products, I can build an automaton of the product, or I can build the automaton or the machine or the station. So we have different models representing different things of the same systems. And so these models are consistent and isomorphic. And then you see the software. And finally, we have the digital objects. This is the sterilization center in which we have the objects, the stations automatically created. And then we have a decision making here, because we are using the simulation model to make decisions. In the case of sterilization center, we are producing the optimal, finding the optimal dispatching policies for each sterilization station. And then we check if the policy is being implemented in the real system. We are using conformal checking. I forget to mention that to discover the models or to mine the system, we are using process mining technique. Conclusion, we are developing a platform that is managing data and models in the most automated way. So from data, we have models, and then we make decisions. All the code that we developed is available on GitHub, of course, with comments. The components, these are general code. And then, of course, the code is customized for the use cases, like for the sterilization center is already customized. We are doing the fine tuning of the models. We are customizing for the plastic. And each use case in the end of the project will test the digital twins generated from data. And let's say the business value and all the impact of the digital twin that is automatically generated, and it is supporting a decision. So we are also closing the loop in the physical system, will be assessed in the last 6 months that are starting in 1st of June. That's all. This is the consortium that you see here. This is the last General Assembly in Milan.
What approach are you taking in your knowledge graphs to ensure consistency and interoperability? Are you making certain commitments?
Yes. In there, when we move from data to knowledge graphs, so we are, first of all, we had to use domain knowledge to build a knowledge graph. And here we are introducing a semantic. So if, for instance, we are cleaning the data, if a data we know that is missing, we infer from other events, because we are collecting events that have a timestamp, an ID of the case, and there is the sensor that stamped that timestamp. Okay, and so we are adding a semantic. But of course, you must have a domain knowledge. You cannot take any data and generate a model. Okay, with the domain knowledge, we add the semantic, and so all the things related to, let me say, graph retrieval data, graph database, knowledge graphs, we are using. Eindhoven is leading this task, University of Eindhoven.